Alright, gang, here we go. So this is Physics Unit 5. We're talking about, or Unit 5, Part 1. We're talking about temperature, and we're going to define heat. Okay, so you got to be kind of careful. You should probably be used to this by now, but in physics, a lot of times they have the same vocabulary for physics terms as we do for everyday terms. However, because we're talking about physics, the everyday definition you're used to might be a little bit different than how we would use the term in physics. All right, so just heads up, pay attention. Okay, so first of all, suppose you have 2 cups of water and one is hot, one is cold. Okay, so how is the cold water different than the hot water? And really, where we want to think about the motion of the molecules. All right, so hopefully you remember from your Chem 1 days that we made a big deal about talking about how temperature or heat or the energy of the molecules is really composed of their motion. Okay, the hotter the object is, the more the molecules that are making it up are moving. Okay, and so the hotter you get it, the more they move, and et cetera, et cetera. So because of that, really we get this term temperature. Okay, and temperature is a measure of the average kinetic energy of the particles. Okay, so when you take a thermometer, stick it in your substance, and you read the temperature, essentially what you're doing is you're reading the average kinetic energy. Okay, number one, we use the average because literally there are thousands of molecules, millions and billions of molecules that are bouncing around in there, and so taking an average is really a pretty decent way of keeping track of what's going on. And then we use speed, okay, because we don't really care what direction these molecules are heading, we just care about how fast they're moving, right? And we know that because kinetic energy, is equal to 1/2 mv squared, this squared term will turn our velocities into a positive value automatically, so we'll automatically get our velocity, or our speed, all right? Now, a new term here is this idea of internal energy. Okay, internal energy is literally the energy that's inside the article, or the whatever substance you're talking about. Okay, so the internal energy is the energy internally. Okay, we use the symbol for internal energy is a capital U. Okay, capital U for internal energy. All right, and it's composed of 2 things. It's composed of the motion of the particles, really the kinetic energy, and then the position of the particles, the potential energy. All right, so these are like the basic forms of energy that all things contain. Okay, we can have translational energy, rotational, and vibrational energy. In translational energy, we literally have something moving from one place to the next, and this is kinetic energy. In rotational energy, the object is literally rotating. So in this guy, this molecule here is translating, and he's rotating. Okay, and here they give some examples of these things, and this guy is also kinetic energy. All right, now vibrational energy is a little bit more interesting. Okay, this would be like you pluck a guitar string and it starts to vibrate, or if you have molecules, they can, the bonds in them will actually stretch and bend and twist, so on and so forth. And so because of this, you get kinetic and potential energy. Now the kinetic energy is because the bonds are stretching, right? They go out and they come in. Okay, so you get movement. Now, bonds at the same time are they kind of like in this regard act like springs. In a spring, you can take that spring and you could stretch it or compress it, and you know that you've created potential energy in the form of elastic energy, right? And so the same kind of idea occurs with your chemical bonds. As your chemical bond stretches or moves or twists, then you end up with potential energy being stored that way. All right. Now we also have to talk about this new term here called thermal equilibrium. Okay. Thermal equilibrium occurs. Now you should remember from chemistry that equilibrium is when you're at a state of rest, right? Your changes equal to one another. Okay. And so thermal means heat. Okay. So we're talking about the temperature or the heat being equal. Okay, and so really what this is that when you reach thermal equilibrium, you've got 2 bodies or 2 substances that are in physical contact with each other that have identical temperatures. So that's the definition of thermal equilibrium. So if you take a hot metal block and room temperature water, right? You take the hot metal block, put it in the room temperature water. The water will heat up because the hot or the energy from the block will go into the water, and the water temperature will rise, and the temperature of the block will go down because it lost energy to the water. Okay, and when they stop changing, their temperatures will be equal. They're at thermal equilibrium. Okay. Now, why is this important? Well, thermal equilibrium is where everything's always headed. You're always going towards thermal equilibrium, and it's happening all around you all the time. You're just not used to looking for it. Okay, a really good example of this is taking the temperature of something. Okay, in order to read the temperature of whatever substance you're talking about, you need to let it reach thermal equilibrium. So if your mom ever or your dad ever took a thermometer, right, one of those old school ones that beep that go under your tongue, not the cool ones that go on your forehead or go across your forehead or anything. I'm talking about the ones that go under your tongue. And you stick that under your tongue, and then you press the button and it beeps, and then you have to wait like 45 seconds or a minute while it reads your temperature. Now, the reason that takes a while is because that metal bit at your end, on your end there, is waiting until it reaches thermal equilibrium with your mouth. Your mouth is hotter than the metal that was room temperature. You put it in your mouth, and the heat from your mouth is going to make the temperature of the metal end of your thermometer go up. And once you reach thermal equilibrium, then the thermometer will actually be able to tell you the correct temperature. Okay, and so once the temperature has stopped moving, that's when it can tell that it's reached equilibrium, and you know the exact temperature of your substance. Okay. Now, thermal expansion is an interesting idea. Okay, during class we did this ball and ring demo. I suggest you just Google ball and ring demo. You know, find a cool YouTube video of this. I Googled this. All right. Okay, and so in class, essentially, it's you take a ring made out of metal and on a big long stick, and then a ball made of metal on a big long stick, and you're heating them up, and you're showing that as you heat up one versus the other, the ball either will or will not go through the ring. All right, and the idea is that as things get hotter, they expand. Okay, so for example, paint specifically is designed for the surface that it will cover. Okay, and so thermal expansion causes the paint to change, and if the paint hasn't been designed properly for whatever you're putting it on, it will expand or contract at different rates from the thing that it's sitting on. So outdoor paint specifically is especially made to go on like the siding on your house. Okay, so the siding on your house will expand and contract as you go to winter versus summer and the changing seasons and so on and so forth. And the paint that you put on that wood also has to be able to expand at the same rate. Otherwise, you'll end up with cracks. Okay, if they expand or contract at different rates. Now also, like the concrete slabs in your for your sidewalks, you notice that they come in like 3 or 4 foot blocks. Okay, like there's 3 or 4 feet, and then there's a crack, and then the next block starts, and then there's another crack, and then et cetera, et cetera. Those cracks are there because they're compensating for the fact that during the summer the concrete blocks will push together and get closer together, and during the winter months they'll spread apart. Okay, if those weren't there, then you'd end up creating like little mountain ranges, right? Where you had one solid piece, and then it got bigger, or it got hotter, so it got bigger, and they would push each other up, kind of like tectonic plates, forming mountains. Now, in order to measure temperature, there's lots of different ways but the one we're focusing on here is using that idea of thermal expansion to help us measure temperature. So here you've got a thermometer that's got mercury in it, and lots of old school thermometers used mercury because mercury is an element and it's metallic, so that means it's really heavy, has a consistent density, okay, and but it's also poisonous, so that's why we don't use it very much anymore. But anyway, so what they do is they take a bunch of mercury, they stick it in the bottom, and they put the thermometer in a substance where they know for sure what the temperature is. So in this case, they put it in something, and they knew it was at exactly 0 degrees. All right, and then they take it and they make like a little mark saying, okay, this was 0 degrees, and then they put it in something else, and because thermal expansion, they put it in 50 degrees. It was in 0 before, now it's in 50. That means it'll take up more space. It expands. Okay, so when that occurs, the mercury will take up more space, so it spreads out. All right, so it comes up here to 50 degrees. So, and then they make another mark. It's like, okay, that's our 50. And then they just kind of break it down that way. Okay, so essentially the change in the length of the liquid column is proportional to the temperature. All right, so you can actually set up a ratio. All right. The temperature scales, lots of these should be very familiar with you from Chem 1. All right, Fahrenheit scale is based off of silliness. Okay, so I'm pretty sure it's based off of the freezing and melting point of brine. But anyway, so the ice point or the freezing point is 32 degrees Fahrenheit. The steam point or the boiling point for water is 212 degrees Fahrenheit. Celsius 0 and 100, and Kelvin 273.15 and 373.15. Notice that the difference between the freezing and the boiling point in Celsius and Kelvin are exactly the same. Okay. So Celsius is used in these cases here. All right. And then Kelvin is used in these guys here. So primarily in chemistry, exclusively in chemistry, we used Kelvin. In physics, we can kind of get away with using Celsius a lot, but we also care about Kelvin, so you kind of need to be familiar with both. All right. This is the absolute temperature scale. So what does it mean by absolute zero? Absolute zero occurs at 0 Kelvin. Okay, and so at zero Kelvin, this is defined as absolute zero. This is the coldest thing, or the coldest theoretical temperature that we could actually get to. We've never actually gotten there, but we've gotten dang close. I think the record is like somewhere around 1 times 10 to the negative 16th Kelvin. So this is something like a point and then 16 zeros and then a 1. So it's ridiculously cold. All right. But essentially the idea is that we know it exists, or we can predict kind of some of the properties there by kind of extrapolating what's going on. So in this graph here, we've got temperature and pressure, all right, and we've graphed it. As we change the pressure, the temperature went down, or the pressure goes down, the temperature goes down. We kind of follow this curve as we go down, and we can extrapolate that if we get to 0 pressure, we also have a 0 Kelvin. We're at absolute zero. Okay, so that's kind of the general idea of that temperature scale. All right, here's a couple of formulas that you need to know about temperature conversions, being able to convert Fahrenheit to Celsius and Celsius to Kelvin. All right, so take a pause, write those guys down. Let's do a couple practice problems and we'll call it a day. All right, so one day it was negative 40 degrees Celsius at the top of Mont Blanc and negative 40 degrees Fahrenheit at the top of Mount Whitney. Which place was colder? Now we know the answer right here. I didn't block it out as negative 40 equals negative 40. So they should be exactly the same temperature. But let's go ahead and convert one to the other. So let's convert Celsius into Fahrenheit. So we know that the temperature in Fahrenheit is equal to, like, let's see what it said, 9.5. So I guess I should use a capital F for Fahrenheit. 9/5 TC plus 32. Okay, so that means 9/5 times our negative 40 plus 32. Plug that into our calculator. We better get times negative 40 plus 32. We get negative 40 again. So at negative 40 degrees, these two guys are equal to one another. All right, so neither of them are colder than the other. All right, we'll do number 2, and I'll let you do number 3 on your own. Okay, it says, what is the Fahrenheit temperature equivalent of absolute zero? All right, so this is a two-step conversion, right? Because we don't have an equation to go straight from Kelvin to Fahrenheit, right? So we need to go to Celsius first. So first we got to convert our Kelvin to Celsius, all right? So we know that 0 Kelvin is what we're at. That's absolute zero. We got to convert that to Celsius. So we'll subtract 273.15. All right, so we're at negative 273.15 degrees Celsius. So we got to convert that to Fahrenheit. Okay, so we'll use this exact same process up here. I'm not going to rewrite the formula. It'll just be temperature in Fahrenheit is equal to 9/5 times our negative 273.15 plus 32. And we get 9/5 times negative 273.15 plus 32, negative 459.67. All right, there you go. So that's it for part 1. Hope you had a great time. Do your practice problems and let me know if you have any questions. I'll see you on the flip side.